Okay, so we are already in lecture number 4, and let's go to the second page. So in the previous lecture, we have discussed about the difference between Laplace equation and source-free Poisson equation. So actually, if we are working with the proper Poisson equation, then source-free Poisson equation should be identical to the Laplace equation or reduced to the Laplace equation. However, as we have discussed already, our Poisson equation typically used in this course is not actually Poisson equation itself. It has an operator which is a little bit modified form, something like this. So since this coefficient in front of gradient of phi is position dependent, so our operator cannot be reduced to the Laplacian operator. It never happens in general cases. So we will think about how can we discretize such kind of situation if we have material inhomogeneity. For example, let's say here we have silicon, and silicon is covered by what? Silicon dioxide. In this case, we have certainly material discontinuity at this interface, and that interface, another interface, also different interface. Here we have obvious differences for its relative permittivity. So how can we determine the value of electrostatic potential for this case? That is the main topic of our today's lecture. Okay, this is just a repeat of our previous lecture, Laplace equation and Poisson equation with source-free condition. We have position-dependent coefficient that makes certain difficulties. For example, if we have this operator for f, and which is evaluated at xi, can be well approximated by delta x squared here and fi plus 1 minus 2 fi plus fi minus 1. That was possible. However, if we have something like this, so epsilon, which is still position dependent, and df over dx, then if we have to evaluate it at x equal to xi, then what is the required coefficient for example, f sub I plus 1, f sub I, and fi minus 1? What is the required coefficient for each of them? So that is our question. So of course, we can think about formulating the coefficient for different cases, but we wanted to do it more compact way and more unified way. So instead of thinking how can we treat this typical operator for certain cases, we wanted to make it general. Okay, so if you are with me, then let's go to the main contents. So I guess that this is already our example. So therefore I have to write down my note here to think about how can we proceed. Okay. Please remember that our Poisson equation has the form like this. It has overall divergence operator and it should take a certain vector. And here the vector is made of certain gradient operator. So that makes a certain vector and we have position dependent coefficient. This is the general form of our Poisson equation. Of course here we have something, yes, here is something, but for a while just concentrate on our left hand side. This is a right hand side. Okay, so if we have this operator, so this operator actually appears very frequently in our entire semester. Later you will see actually this form occurs even in other cases. I mean that. Let me slightly generalize it. Here we can say, oh, okay, we can say there is a certain vector here and that is corresponding to a source function. Can you recognize the generalization for this Poisson equation to more generalized form? So then in this case, what is f? So f is simply given by epsilon multiplied by gradient of phi function, and also here source function s is identified with minus rho. So if we have this generalized form of a certain operator, let's work with this form. If we have to solve this equation, or we have to discretize this equation, how can we do the discretization? I wanted to suggest this form. You know, this form is written in differential form. So here we have differential operator, and yes, therefore a differentiation of certain vector involves a scalar field. That is the form of our usual partial differential equation. So if we consider two-dimensional or three-dimensional space, then that becomes the partial differential equation. Then instead of considering this differential form, I wanted to suggest to you to work with integrated form. So how can we make an integration form from this differential form? In this case, I wanted to suggest to integrate our entire equation, both of the left hand side and right hand side, over certain range. Here, let's do that together. When I make integration over certain range, then let me integrate it. Then divergence of vector f is integrated over certain range, and also the right hand side we have to have, so integration over s over certain range, the same range. Okay, so then let's say this is given by this integration domain is given by omega. So what is omega? Omega, let's say we are considering three-dimensional structure, then and let's say this is so origin of our coordinate system, and we wanted to make make the discretization around a certain position. We have a position Ri, and this Ri represents a certain position, and we wanted to make a discretized version of our differential equation. How can we make a differentiation? So in this case, I will introduce this omega 4 Ri as a small box surrounding the Ri position. Okay, so if we have a certain position, the target position to be discretized, then we will introduce a small volume which contain the Ri position. So can you visualize it in your brain? For example, if we are working with simplified two-dimensional case, x and y, then let's say this is our origin, and say we have still uniform grid like this. So we have a position, we have a position, position. So grid points are located in these points. So there are many available points here, and if we wanted to make the discretization around this point, then we wanted to introduce our omega, for example, like this. Then this omega just containing only one point, I mean that only one point is surrounded by this omega volume, and all other points are excluded in this omega range. So what can we expect is, since the integration is performed only over the position Ri, then the information extracted from this integration is more or less related to this Ri position only. For example, information for this position far away from Ri cannot be obtained from this integration, because we have restricted our integration domain to the small volume around Ri. So since we have restricted our integration over small domain, all information obtained from this discretization will be related with that center position. That is my point. Okay. Now we understand this omega is just localized around Ri. So small box is considered for this integration. So now let's consider the right hand side. Right hand side is just kept as before. We will just make an integration over Ri. So because this is just an integration of a scalar function that can be easily approximated. But please have a look at the left hand side, our differential operator involved. In this case, we don't want to evaluate this divergence operator directly. That is the main motivation of our today's talk. So instead of considering this divergence form, we wanted to reformulate it with the help of Gauss theorem. So with the help of this Gauss theorem, here we have divergence of a certain vector, and that divergence is integrated over certain volume. And you know that this integration can be easily transformed or changed to the surface integration. If we apply Gauss theorem, then now it becomes, instead of this volume integral, now we can introduce a certain surface integral. So surface of what? Surface of our omega. So omega, let's say that if we have a small box omega like this, then of course it will have the surface, 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 surface. So it will have 6 faces, and the collection of these 6 surfaces are denoted as A, capital A in this notation, and we can make, and now we have f function. Okay, so this is Gauss theorem, and here we have actually the A component. So the A here should be regarded as small dA, the infinitesimal area on the surface, and multiplied by the out normal direction n. I mean that here if we have omega, then dA component should be regarded as small dA, and its direction is out normal direction for this top surface. If we have this surface, then okay, we can introduce an infinitesimal area dA. Also, that our normal direction should be something like this. This should be the out normal direction. And of course, I understand when I denote so volume integral, actually I have used something like dr, but this is not actually the vector notation. It should be regarded as dx, dy, and dg. This vector notation is somewhat confusing, but please understand this is introduced that this r is not just one single number, but we have to keep in mind the combination of dx and dy and dv. A better notation can be, for example, we can introduce like dv, but I will just keep my notation in this semester. And now we have arrived at this integrated form. And yes, in this case, the main advantages of this integrated form over the differential form, the original differential form, is previously we have to consider the divergence of a certain vector field at certain position. But in this case, now we don't have to make the differentiation. Okay, that is quite obvious, because previously there was a derivative, but since we have done the integration, so there occurs no derivative. So we don't have to think about the derivative explicitly. That is the main beauty of this integrated form. Then where we have to evaluate the f function. So f function at r sub I is required? No, certainly not, because it should be evaluated on the surface area A. We have to, for example, let's say at the center of this box, we have Ri. Can you see it clearly? But that is not the position where we want to evaluate the f function. We wanted to evaluate the f function at, for example, this surface area and that surface area or that surface area. So let me just be more specific. So think about this one. Please introduce a triplet like I, j, k. So in order to represent a certain position which is given by, for example, delta x times I and delta y times j and delta g times k. Let's say this is our position of interest. Then my question is, should we have to evaluate the f function at r? Obviously not. We wanted to evaluate the f function not in this original r position, but possible position for evaluation would be just delta x multiplied by delta x multiplied by I plus half and delta yj and delta g k. We wanted to evaluate the f function at this point. This point is, for example, if this is corresponding to R or our center position R, then this is corresponding to if this is x direction, y direction, and g direction, and this point is just a half index away toward the positive x direction. Or we wanted to evaluate the f functions at, for example, I minus half, which is a half index away toward negative x direction. And by repeating this operation, now we can think about 6 surrounding neighbors for our R point. Say we have R, the center position R, then we can think about a slightly positive along the x direction and slightly negative along the x direction, and also let's say along y direction, also along g direction. We can think about this point which is slightly deviated from the center position. Why are I talking about this 6 representative position? It is only because these are corresponding to the center. Oh, my drawing is too ugly. So, okay, but please, yes. So these 6 points are corresponding to the center of our 6 surrounding surfaces. So if we adopt, for example, this kind of box, so although omega itself can be shaped in a general way, but for while, just to assume that this is just a cuboid, then we will say this left hand side can be decomposed into a sum of 6 different sums. That here we have surface, 6 surfaces, so surface number 1 up to 6, and we can calculate this way. Now we have to calculate A for certain surface and dA multiplied by f function. What is the difference between this the original form and decomposed form? Previously here A takes all 6 surfaces around a certain position. However, now we have decomposed that into 6 surface-wise integration. So for each surface we take the integration, and for all 6 surfaces we can just make a summation over different surfaces. Then if we take this operation, then now this boxed area, this can be easily approximated. So surface, since we have a given surface, then this integration over A surface now becomes just area of A surface. So for example, if we have something like this, then this area becomes just delta y multiplied by delta g, and this surface can be, for example, delta x multiplied by delta y. In this case, these numbers can be used as the surface area of our surface, and we have here dot product between dA and F, and think about this top surface. Here we have F function, then this F function can be evaluated at the center of our top surface. So how can we understand the position of this top surface representative position? It can be easily interpreted as delta x times I and delta y times j, and finally delta g times k plus half. So this plus half represent the position for top surface. So in this case, I wanted to say, why don't you write down this way, f. However, since f itself is a vector quantity, so we have to keep in mind that only we have to take the z directional component. If we have an x directional component over y directional component, that will be masked by dA product. Since dA is a vector quantity and its direction is out normal of our surface integration. So since this is correspond aligned z directional unit vector, so we have to take into account only a z directional component. So, and that is just evaluated at So delta xi, delta yj, and finally delta g k plus half. That is the required evaluation. So then let me just go to the notation. So we have 6 surfaces and area of 6 surfaces. And here we have, for example, in this case, we have to have Z for top surface, but if we are considering this surface, then we have to think about fx component only. Also for this surface, we have to consider fy only. So say that anyway fn. This n is regarded as anyway abnormal direction. And we have to introduce certain index I, j, or k, and one of them is just plus minus half index away from its original one. So let me just write down. For example, if we are still considering this box, then why don't we just do the first x directional, y directional, and z directional surfaces. For example, let's consider this first surface. In this case, we have to consider delta y, delta g in order to evaluate our A surface, area of a surface, and multiplied by fx evaluated at I plus half j k. Also, we have the opposite surface. Okay, in this case, our normal direction is not positive x, but it is negative x. So we have to add again delta y, delta g multiplied by f minus x direction and I minus half j k. Of course, the component along minus x direction can be regarded as component along positive x direction with negative sign. So we will have simply this form. This is related with x directional surfaces. So why don't we just repeat it for example, y directional surfaces whose abnormal direction is y directional unit vector or minus y directional unit vector. In this case, we have to introduce area delta x multiplied by delta z and multiplied f y directional component and I comma j plus half and k and minus delta x delta z multiplied by f still y directional component and I comma j minus half k. And finally, let's go to the z directional component. And when you go to the z directional component, then area should be delta x, delta y, and the component is z directional component. And evaluation should be performed I, j, k plus half, and also we have minus delta x, delta y multiplied by fg I, j, k minus half. This is the explicit form of our integrated equation. So we have started from this differential form, and we have made an integration of a small box omega, and we have assumed uniform spacing along x direction, y direction, and z direction, and for a given box, the explicitly evaluated left-hand side just looks like this. Then this is, up to now, we have talked about the left-hand side. Then how about the right-hand side? Right-hand side was just integration of our source function over our small volume omega. So therefore it is well approximated as a scalar field who is centered at I, j, k index, the position Ri of our interest, and multiplied by the volume of our omega box. So delta x, delta y, and delta g, that is enough for this integration. So we will have this kind of integrated form for our original equation. Okay, so therefore, since this is more general form, since the form we have considered up to now is even more general than Poisson equation. So by just inserting our epsilon multiplied by gradient of phi as the f function, we can easily recover the discretized form of our Poisson equation. Why don't you just do it together with me? Okay, so let me concentrate on only a left-hand side now. So, okay, we can work with this one. Delta y delta z. Now, here, this is the left-hand side, and this is discretized, and we wanted to work with it. F is, in the case of a Poisson equation, it was epsilon gradient of phi. So then what is fx? X directional component of our f vector. Then of course we have to multiply the x directional unit vector and take the dot product to extract f sub x. Then we just do it, and epsilon gradient of phi. So now we have introduced the specific form suitable for our Poisson equation. In this case, f function is simply given by epsilon and gradient of phi. And since we wanted to have fx, fy, and fz component, then they can be easily understood as epsilon lambda phi over lambda x and epsilon lambda phi y, and finally, yes, we can say in this way. Then left-hand side of our Poisson equation is given by, for example, delta y and delta z, the area of our surface, and fx component, which is defined as I plus half index and j and k. So of course it has 5 other components, but for y, just concentrate on the first one. Then now we have to evaluate this first term as epsilon, which is developed or which is evaluated at certain position, half indexed position between ijk point and I plus 1 jk point. Okay, since this is not located at the integer indexed position, so for integer indexed position, we have a possibility to have an interface node. However, if we have half indexed position, then it is certain that this point never belonging to the interface. It is always belonging to a certain material like a silicon or silicon dioxide. It is because if we have a certain interface, then usually we assign the positions or grid points in order to definitely define the interface position. Every interface points are indexed as a regular grid points. So therefore, the artificial one or some virtual one, which does not exist in reality, something like a half index one, that cannot be the interface node. So it means that there is no ambiguity about the epsilon value for this one. Here, this can be either silicon or silicon dioxide if we consider a system where silicon and silicon dioxide coexist. So there is no ambiguity for selecting epsilon value, and we have to evaluate now partial derivative of a phi function at position of I plus half and j and k. Okay, although we have previously considered only one-dimensional cases, but we can easily expand our previous one-dimensional discussion to this three-dimensional discussion. It is because this j index or k index, index for y and index for z, are kept as before. So please note that we are now considering I, j, k index, and these are the same, and this is the same. So only x directional component has a little bit shifted. So we can treat it as just one-dimensional version. Then how can you do that? So this one now becomes delta y, delta z, and epsilon I plus half j k. And here we introduce the same technique, delta x and phi evaluated at what? I plus 1 j k minus I j k. That's it for the first term of our Poisson equation. Okay, this one can be specialized for the Poisson equation in this way. Of course, we will have subsequent terms like this. For example, if we consider the negative component, then delta y, delta z, and epsilon evaluated what? So evaluated minus half j k, and here we have delta x, which is given by phi I minus 1 j k minus phi I j k. Oh, I made a mistake. So you have I, and here I minus 1 j k is required, and we have 4 more terms corresponding to the 4 other surfaces. These are 4 surfaces normal to x direction and normal to y direction and normal to z direction. Each of them is 2 different terms, and when we collected them all, we will have 6 different terms for our cases. So now we have finally obtained the discretized Poisson equation, even valid at 3-dimensional cases. Let's make a specific example. Up to now, we have discussed about the general dimension, 3D, and of course, we can reduce it by just neglecting certain directions. For example, if we are working with a 2-dimensional structure, then what will happen? In this case, we can certainly just neglect the term related with g-directional derivatives. And 1-dimensional case, we can safely say, if we neglect, y-directional derivative and z-directional derivative, we can get the Poisson equation, which is valid at 1-dimensional case. So why don't we do that in this case? Then, if we are talking about now 1D case, then previously we had 4 more terms, but all of them are gone. So there is no other terms at all. So these 2 terms are all we have. And delta x and delta y. What is delta x and delta y in this case? Since we have no further discretization on yg surface, we can treat it as delta y and delta z as just area of our sample. So think about the situation we are considering right now. This is 1-dimensional structure. So we have a 1-dimensional structure laid on x-axis, and we have the cross-sectional area of our structure, 1-dimensional structure. So this is corresponding to our delta y and delta z. So we will just write down as just area A. Then now it becomes just something like this: A times epsilon I plus half and delta x phi I plus 1 minus phi I, and minus epsilon I minus half and delta x phi I minus phi I minus 1. That's all for our 1-dimensional case. So now let me just write down the final form for 1-dimensional Poisson equation, integrated form. Then since we are talking about the source-free condition, so the right hand side just vanishes. So our Poisson equation, source-free Poisson equation now becomes area and epsilon I plus 1 delta x. I'm just repeating the equation below. I minus 1 equal to 0. This is the source free Poisson equation integrated over small volume. Okay, then later, how can we normalize it? So in the lecture material or preview lecture 3.5, I just eliminate this a function, just divide the left hand side and right hand side by a, and multiply delta x to the left hand side and right hand side. Then eventually we have epsilon I plus 1 phi I plus 1 minus epsilon I plus 1 plus epsilon. Oh, I made a mistakes here. Oh, sorry about that. Here half and half. Sorry about my mistake. Here half I minus half phi I plus epsilon I minus half phi I minus 1. This is really the final scaled version of our source-free Poisson equation. So now we have arrived at this N5 example. So if we have N5 example, you can easily understand if we have material 1 internal, if we are considering just a node certainly belonging to epsilon 1 or material 1, then we have epsilon 1, and 2 times minus 2 times epsilon 1. Or if we are working with a position certainly belonging to material system 2, then we have epsilon 2, and minus 2 times epsilon 2. However, if we are working at the interface node whose left position and right position are belonging to different materials, then we have to think about the epsilon 1 and epsilon 2 for these two off-diagonal components, and sum of them, epsilon and 1 and epsilon 2, is given here with negative sign. So I think that since we have already discussed more general cases, so this simple example in the 1D and small number of points is quite easy to understand for you. So I think that we have covered all required contents now, and please come back to our example. Here we have discussed about one simple example, which is a combination of material 1 corresponding to silicon and material 2 corresponding to silicon dioxide. Please do your exercise following the preview lecture, lecture 3.5. I have shown to you everything required for this exercise. And the difference between our today's live lecture and the preview lecture 3.5 is, in this preview lecture 3.5, I have stick to one-dimensional structure, and instead in the live lecture, lecture 4, I have introduced more general three-dimensional cases. So I think that you can watch both things in order to enhance your understanding on the subject. But I guess that today's presentation is much more generalized. And you have the final homework. So can I write down is way? No, I cannot write something here. And here you have homework number 4, and please do it by this Wednesday morning. So you have just around 46 hours. And now consider a heterostructure, 2 layers and a very thin silicon oxide layer and relatively thicker hafnium oxide layer, and all related material parameters are given here, and just to calculate the capacitance per area, it should be written in the unit of farad per square centimeter, and you have sufficient knowledge on to calculate the capacitance per area with analytic expression. You have done it in your general physics course, I guess, and you have done it for all other things like other courses like electrostatics or something like that. So you can calculate the analytic expression, and please do your numerical exercise. Of course, you can follow this way, this N5 example. However, since now you have different thicknesses for silicon dioxide and hafnium oxide, the easiest way is to just introduce many points to discretize this 0.5 nanometer and 1.5 nanometer at same time. For example, if you introduce 0.1 nanometer spacing as a delta x value, then everything will be perfectly fine. So with that one, please solve the system, then you will get electrostatic potential, and from that electrostatic potential, please reconstruct the displacement vector or the x directional component of x directional vector. Then from that displacement, you have applied 1 volt and you get certain displacement. Then from the ratio between them, you can easily calculate the capacitance, and please make a comparison between your numerical calculation and analytic expression. Okay, that is relatively simple homework number 4. So please do it and submit by tomorrow morning. Okay, I think that I have covered everything required for today's lecture. See you Wednesday. Bye.